So good morning, everybody. My name is Tim Pennucci, and morning. And I'm a postdoc at Utrecht University in Budapest, Hungary. I'm part of Nanograv and the IPTA for a long time now, and it is my distinct pleasure and honor to tell you about pulsar timing. Brief introduction and overview. It will be a bit meticulous, not comprehensive, and unfortunately I won't get to any of the truly interesting, awesome use cases. Andrea Lohman and Maura McLaughlin will tell you about these things later in the week. But first I'd like to thank Balchandra, the LOC, the SOC for having me and giving me this opportunity to lecture you about pulsar timing. I've been allotted 90 minutes of time, which is a lot, even though, there are textbooks written on this subject. 90-minute lectures are difficult to sit through. So I encourage you strongly to stop me anytime I don't make sense, which probably already happens. Please ask questions. Sometimes I'm staring off into space, so you can be polite and do this. You can be a little less polite and do that. Or you can just say, hey, do one of those things, please. Because otherwise, you'll lose your attention, I will lose your attention, and maybe that's justified. But I will, in turn, ask you a couple of questions over the course of this lecture. The first few are, I think, the more challenging ones because they come earlier in the lecture. So, you're still with me. Maybe by the end, those questions are going to be just like, are you awake and still paying attention? But I hope it's worth your while. So let's start this journey. This slide is a very terse slide that just tells you some of the resources that I've drawn upon. I've taken a lot of graphics and ideas and slides from David Nice, who you'll meet next week. We're staying for the science meeting. These two textbooks are some of the go-to handbooks in our field. They describe not just pulsar timing, but basically everything, a comprehensive, mostly comprehensive overview of the field as of, well, maybe less than 10 years ago now. I mean, they're still very, very useful resources. If you don't know them, get to know them if you want to know more about pulsars. Nanograv has put together this amazing glossary. I have had nothing to do with it, but if you want to jot this down or take a picture of it, you can pull it up now if you get bored. It's, I don't remember, 30 pages of pulsar and astro terminology. Even if you just look at this ahead of next week, you'll be head and shoulders above the unprepared, I suppose. And of course, there are numerous references that I cite within the talk. This is not so much of an outline as of a list of questions that I will attempt to answer. And there's really only 3 of them, and that's why this talk will appear meticulous at times. It's basically just, what is pulsar timing? I mean, if I can drive this point home in a very, simply pedagogical way, I'll be happy and have done my job. All the rest are, details and higher level understanding. But if you just get the notion of what is it that we're doing, that's important. And then, of course, more meticulousness of how those times of arrival are measured. What are these TOAs, and how do we actually measure them? And of course, almost more importantly, what makes up a timing model? How do we describe the arrival times? How do we predict the next one? And what goes into that, and what goes into that process? And originally, I had intended to cover the interesting parts, right? The use cases. What do we use pulsar timing for? Why is it, in my opinion, the most awesome tool in all of astrophysics? But like I said, you can expect to hear those interesting topics from Andrea Lohman and Maura McLaughlin later this week. So let's begin with this image, and this is a picture not of a pulsar. Let's not confuse the map and the territory. It's just our friendly cartoon image of what we like to envision in our minds when we think of a pulsar. You have that tiny, very dense neutron star in the middle, about which you heard a lot yesterday in the first talk. Very large magnetic fields, which we like to pretend are very dipolar, at least far from the neutron star. And this whole thing is set in motion around the spin axis. And when you have that offset magnetic axis from the spin axis, you will get acceleration of particles, that plasma pair production, and in some detailed sense we don't understand just yet, you get radiation across the spectrum. We see a lot of these objects in the radio, but we also see them in many other wavelengths, as you heard yesterday. And I think it may have been Vicky Casby who first referred to this as the pulsar zoo. So you will encounter very many different kinds of pulsars as you enter this field. You have your classic radio pulsars, those first things that were detected, the slow ones that have 1 second periods. Sometimes they're called canonical pulsars. The really interesting ones are the millisecond pulsars. They're fully recycled. So after there's stellar evolution in a binary, there's accretion. You heard this also yesterday. And that spins up some pulsars to millisecond periods. Also, one of the first kinds of pulsars that were discovered were the young ones, because you could just point your telescope at a supernova remnant and expect to see something, or hopefully to see something. And in Crab and Vela, you do see pulsars, and they're a slightly different class from these two. You also have a fourth general class, the magnetars. You often see them in X-ray, but there's a handful, I think 5, maybe 6 now, that are seen in the radio. You have these spider pulsars, black widows and redbacks, with very special kinds of binary companions. You have double neutron stars, which is sort of one slow pulsar. Well, two neutron stars, but there's one double pulsar actually, which is a sort of slow pulsar and a partially recycled pulsar. And those are also kind of the special class of pulsars. You have X-ray pulsars, which could mean basically anything. You just see X-rays coming from a pulsar. It could be thermal, it could be non-thermal. You have accreting millisecond X-ray pulsars. So a binary system which is actively undergoing accretion, and you might see X-ray pulses from spin periods that are at the millisecond level. X-ray dim isolated neutron stars, that's basically a nearby set of neutron stars that we see X-ray modulations in thermal X-rays. Gamma ray pulsars, and this last one, gravitational wave pulsars. I haven't seen those yet, but LIGO, right, is looking for signals from rotating neutron stars. And if they were to see something, that would sort of be a gravitational wave pulsar, right? This not seen yet, but I should hope at least in the next generation LIGO-like observatory, they would see such a thing, and that would be a new class. The point here, though, is that you can time all of these. Pulsar timing is general, very general. And you may choose to time these for different reasons. Mostly, we like to time millisecond pulsars because they're the best clocks, and we'll come back to why that's the case. So just putting that cartoon image in an animation, I'm sure you have this in your mind already, but as the neutron star rotates and the beam crosses your line of sight, first you see nothing, 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 and then a blip of radio emission, and then nothing again. So you get this blip roughly once per rotation, and that's very much like a lighthouse. And the first take-home point is that you can time these pulsars because pulsars are clocks. So you have this cartoon image, rotates around, blinks like a lighthouse, and that blinking is just like the ticking of a clock. Here I'm showing you what's called a pulse profile, or an average light curve. You'll see a lot of these. I think we saw some yesterday. You'll play with these in the activity sessions. And it's from a very special pulsar in a globular cluster. But this is showing the average radio emission at roughly 1.5 gigahertz for this pulsar as a function of rotation. So this is, the neutron star pointing at you in some configuration and making 360 degrees rotation. And this single tick is actually kind of decomposed in 3 little sub-ticks or sub-flashes, if you will. And the name of the game in pulsar timing really is to measure these observed pulse profiles and locate them absolutely in time with respect to some other clock or some time standard. And that measurement we call a time of arrival. That's sort of one tick of the clock. Let that sink in just for a second. Now let me give you a very practical take-home, write-it-down kind of definition of pulsar timing, which I think I attribute to my graduate advisor who got right, so I'm not positive. But so pulsars are clocks, and here's your definition for pulsar timing. It is the unambiguous accounting of each and every rotation of a neutron star. Okay, there's nothing like this anywhere in astrophysics, as far as I know. I mean, it's bizarre if you think about it. There's this 2 solar mass object, thousands of light years away, spinning hundreds of times per second, and we're bold enough to claim that after making some kind of timing model for how this thing rotates, we can look away from it for years, and we can count every single one of those rotations, and then come back and make a prediction for the arrival time of the next one. So here's the example from one of the most well-timed pulsars in the business, 1713 plus 0747. This is over a 21 period from this paper here. The first pulse in data set was observed. I'm not going to ask anybody's age, but I'm sure, you know, I was quite young at this time. And it arrived at exactly this, I think this is a UTC time with this level of precision. 160 nanoseconds, and the last observed pulse in the data set was some 20 years later at this UTC time with roughly the same precision, 140 nanoseconds. And based on our model for how this thing rotates, and because we have this thing called phase connection, which we'll get back to, we know exactly that the neutron star rotated 146,495,457,989 times, right? And part of the reason why we can do this is that you can't get a rotation wrong. It's an integer quantity. And just so you know a little bit more about this pulsar, it spins at about 220 hertz, 4.5 milliseconds. And okay, the other thing, the takeaway from this slide is that there's 2 fundamental observables for all of the pulsars: is just how quickly are they spinning, and because they're losing energy, they're also spinning down. So the neutron star clock basically has these 2 fundamental parameters. We'll come back to that as well. So how does pulsar timing unfold in practice? This is sort of the one slide summary of how it works in a very schematic sense. We first observe a whole bunch of pulses, a sequence of pulses. You can count them, 1, 2, 3, 13. And then the next step is you build your timing model. And what that means is you're able to account for the arrival of all of these pulses. So you can already account for what you've seen. And then the next step is to predict the arrival time of some next pulse. So you stop looking at your pulsar, you have your timing model. Next week you say, okay, according to my timing model, a pulse should be observed now. And if you've done that accurately, we say you've maintained phase connection. What that means is that you're able to predict the arrival time of the next pulse, whatever that may be, to within 1 rotation of the neutron star. And you can do this over long time scales. And of course, this is a bootstrapping process. So when your timing model is not perfect, you're going to improve it. You're going to repeat this process until you've solved the clock, until you have no more systematics in your residuals. And that's a lot of terminology we'll come back to. But a little more about phase connection, because this term comes up a lot, and it's important, it's integral to understanding how pulsar timing works. And here's a sort of anecdotal example of what phase connection is in your real life. So, if you go on a vacation in some distant place on top of a mountain in desert camping or whatever, maybe you just put away all your devices, and you get there on a Monday, you go to sleep, you're happy to be on vacation, the next day is Tuesday, you do some programs, Wednesday, Thursday goes by, Friday goes by, and you're like, okay, today's Saturday, and then a week goes by, a couple more days go by, and you're like, is it Wednesday or Thursday? And if somebody tells you it's Friday, you've kind of lost phase connection with the days of the week. You're off by more than a day. And this is really, this is kind of, I think this is a reasonable example. The next set of examples, so this one is a time scale of days. The next one is a little less reasonable, I think, but it's time scale hours. I think we've all had this happen to us. This didn't happen to me this morning, but you know, sometimes you set your alarm and you actually wake up right before your alarm goes off. And that's kind of because you have this internal clock. It's very anecdotal. I wouldn't actually, you know, by chance you expect this kind of thing to happen, but you have some kind of internal clock, right? You get hungry at the same times of day. That's not by chance, right? And of course you have circadian sleep cycles, which can be thought of as being phase connected with the rotation of the Earth. And many of us right now are jet lagged, which is kind of a loss of phase connection, right? We don't know where the sun is all of a sudden. We don't know when to go to sleep. This is an essence of phase connection. But my favorite one is more on time scales of seconds. And hopefully you haven't been in this situation, or maybe you haven't. But you're on the dance floor and you hear the music, and you know you're dancing. You're happy that you're in the beat, and all of a sudden the music cuts out. But you have to keep dancing, right? You don't want to stop. You don't want to stop dancing because the music comes back. And what you're hoping, though, is that you're still in step with the music when it comes back. If you've done that, you've maintained phase connection with the music. It's really that simple in a way. Now, even if you're in step with the music, you have to ask yourself: are you sure that you haven't actually missed the rotation? You haven't missed the beat. But anyway, enough about dancing. We're going to do a quick demo that demonstrates this. I know there will be no dancing, I promise. And the demo is quite simple. Right. Everybody hears this? This is our pulsar. It's an audio pulsar, right? And right now you're observing your pulses, right? And as you're observing your pulses, you're internally building a timing model for how this thing is ticking, how those arrival times are coming. And what I'm going to do is I'm going to count down from 10. And after counting down the 10 pulses, as you can hear, I'm going to stop this, right? And I want you, in your mind, to count out the next 10 pulses. I want you to close your eyes. I don't want you to tap your feet. Don't tap your fingers. Don't be synchronized with one another. Just use your mind to count out the next 10 pulses. And be brave, okay? We all have to be brave today. On the 10th pulse, you're going to clap. Like your life depends on it, all right? None of this stuff, okay? Clap, okay? And make sure you're doing this with your eyes closed so you're not influenced by anybody else, okay? So here we are. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. That's very good. So you see, you're not very good pulsar timers yet. Right? That was quite a large dispersion. That was at least like a one period kind of dispersion. Some people are on the beat, in my opinion, my timing model. Other people a little early. What's that?
We can bootstrap it again.
Yeah. And keep in mind there that you had one parameter to keep track of for just 10 seconds. Yes. It was just the spin period. That's it. Okay? So this is why we need mathematical models to do this. There are lots of parameters, and it gets very complicated. Okay, now I said be brave because I have to do a similar kind of thing now to drive this point home. And you're going to hear some really bad sounding music right now. You're going to hear a drone of music. Okay, and you hear a backbeat, right? It's about 4 hertz. Okay? This backbeat is going to drop out in just a few seconds. And I know it's going to drop out, so after that I have to use my timing model to count out 128 pulses. And on the 129th one, I'm going to buy. Okay? I'm only going to count every 4th pulse, so you're going to hear me say something like 1, 2, 3, 4, 2, 2, 3, 4, 3, 2, 3, 4, 4, 2, 3. failed. It worked this morning. Disappointing. All right, you get the picture by now, I hope. We back in the show here? Back in the show. Okay. So, unfortunately, that did not work. Maybe I'll try again later. And I need this. All right, I can no longer see. Sorry. Okay. Yeah, we're at the beginning. I'm not going to do that again. But, all right, so you get the picture. And, all right, so back to the nuances. I think you saw, okay, yesterday the diagram you saw was period versus magnetic field strength. But here I'm showing you a more commonly used plot, I think, period and period derivative. And I'm choosing this because I told you that these are the two fundamental observables for most of our pulsars. You heard yesterday that there's roughly 2,500 pulsars known. They're distributed in the P dot diagram as so. And you have your two fundamental observables. You heard yesterday that there's an assumption of magnetic dipole breaking because you have an offset magnetic dipole from the spin axis. And based on that assumption, you can infer the spin down power, which are these lines here, constant lines of spin down power, constant lines of magnetic field strength are this way, and characteristic age this way. So you can derive these parameters, but they don't have much to do with pulsar timing right now, so we're not going to dwell on them. But I want you to see that the pulsars fall into four broad categories, which I mentioned earlier. The slow ones, the young ones up here, the magnetars, and the millisecond pulsars. Obviously, you should notice that most of these millisecond pulsars are in binaries. That's why they have circles around them. And for most pulsar timing experiments that are very precise and we want to use for things like gravitational wave experiments, which is why we're all here, you want to use millisecond pulsars. And so why are they the best clocks? Well, I would argue that it's in part because they're the fastest spinning pulsars, and that gives you the highest measurement precision. So all else being equal among two pulsars, same brightness, same amount of other kinds of noise, same distance, all this other stuff is, let's say, is exactly the same. The fact that you're a faster pulsar just means you collect more data per second, and also the duty cycle is smaller in absolute time, so you can locate that pulse in a smaller time window. But empirically, we also see that the lower magnetic field strength pulsars have a lower amount of what's called timing noise, which we'll get back to. But that means effectively that they're more stable clocks. So pulsars in this region of the diagram are the best clocks for high precision pulsar timing. Okay, so here's our pop quiz question 1. This has actually less to do with my talk and just more of a review of what you saw yesterday. So there's a huge dearth of pulsars here, and it's delineated by this line, and it's referred to here as the graveyard. So what is this thing? Is it a dearth of observed pulsars due to observational constraints, or some kind of selection bias? A real deficit in the pulsar population, the place where main sequence stars end up after they die in a supernova explosion, or the place where neutron stars die once degeneracy pressure fails. So take just 10 seconds and think to yourself or ask your neighbor. And then I'll just ask for a show of hands. You can chat. Who thinks it's A? Okay. Who thinks it's B? All right. Who thinks it's C? D? And who is abstaining to vote? I'm putting you on the spot as well. Thank you, Nick. All right. So I would argue, based on we would call it an X-ray pulsar. So in a way, it's kind of both A and B. When you talk to most people, they're going to talk like it's A because they're thinking of just radio pulsars. But we got to be broader-minded than that. So actually, there are neutron stars here, right? This is where they go to die. They evolve down this way. Again, it's not too important for pulsar timing. So let's get back to business. Yep.
Okay. So why the dearth of pulsars above the millisecond and below the normal pulsar? Just where you draw those, no, below.
Here?
Just above that, yeah.
Here?
Yeah. Where you have those age lines, right?
Yeah.
Around there are no pulsars.
Oh, like here?
Yeah.
Ooh, great question. Probably has something to do with the way they evolve, because they're observed to be born up here, tens of millisecond period, probably. But generally up in this region, they have large spin down and relatively short periods. It's very difficult for them to shed their magnetic field or from the magnetic field to decay. So that means they have to move down this way as they spin down along lines of constant magnetic field strength. And then they just die here. But if they have a binary companion, they get spun up out of the graveyard. And what that does, though, is, again, empirically, we see that the accretion quenches their magnetic field, and it gives them higher spin periods. So that means the evolution kind of happens down this way. So you basically just can't really populate naturally pulsars in this way. But I'm sure we can find, actually I think there's a globular cluster pulsar that's like sitting up here. Which one is it, Renee? Do you know?
I don't know off the top of my head, but it's a little bit higher.
Yeah, it's one of the, I think it's a gamma ray pulsar. But you know, there's also systematics in that maybe put it like kind of down here. But there are, I think, a handful that sit here, but there are really none that sit up here, I think. Good question.
If we have more transitional pulsars and a higher sample of pulsars which you detect during the act of accretion, that gap may get explained in future at some point. And right now we have only 3 of them.
Just 3. Okay. So again, yeah, it may just be a instrumentation kind of thing.
One more.
Yeah. Oh, fabulous.
Yeah, what is degeneracy pressure?
Oh yeah. Ooh. That is not part of my talk, but okay. So yesterday morning we heard a bit about degeneracy pressure, or maybe I don't remember if that term was used. But basically, it's a source of pressure that arises from the fact that certain quantities are quantized. So it falls out of quantum mechanics. And in the case of white dwarf stars, you have electron degeneracy pressure, which means even in the coolest possible state of all the electrons, you cannot put any more than 2 electrons in one configuration of location and momentum. So you can have one at a specific point in space with a certain velocity vector, and it can have spin up and spin down. You can't put another electron in that space with that velocity vector with any spin. So what that means, though, is when you add more electrons into the system, they provide a resistance. And that's it's called degeneracy because, that's a good way to explain that. You have to distinguish the electrons. And if you can't distinguish them, that means 2 electrons are degenerate. We can come back to this later if you'd like. In a neutron star, you have another form of degeneracy pressure. Degeneracy pressure in general, though, is something that falls out of quantum mechanics. So, and the take-home, though, is that it provides a resistance against gravitational infall. Okay, back to the show. And I need my clicker. Okay. Nope. So your time arrival measurements, we collect a train of pulses, and we're hoping that the pulse, if we were to plot the at our telescope what the incoming pulses look like, they might look like this. There's some noisy off from zero baseline, and you see a pulse coming once a second. And then, what you could do is just simply, as the pulses, come by, you could write down the time on your clock, but that would be enormously imprecise. However, for most pulsars that we actually want to time, it looks more like this. And this should work as well. There it is. So you actually cannot discern the individual pulses, and you wouldn't simply be able to just measure the arrival time of some peak of a function of your data stream. So what we have to do is you have to fold that noisy time series. And by folding, we mean you're slicing up that noisy time series based on the period of the pulsar, stacking them on top of one another, and basically reducing the level of the noise while increasing the level of the signal. So you get a high signal to noise ratio pulse profile, which is what I'm showing you here. Again, this is a function of, let's say, time or the rotation of the neutron star, and this is the average radio emission for that particular pulsar. So that's what we mean by folded pulse profiles. And as you saw yesterday, you can measure these pulse profiles as a function of time, too. So you can make that average, let's say, every 4 minutes, as is done here. So here's the time axis, 0 to 20 minutes, and individual indices, 1, 2, 3, 4, 5 pulse profiles. And the color scale is coding the amplitude of the emission.
When you don't have when you've just found like the pulsar and you don't have the period yet, how do you fold it if you don't know what time skip, like what period?
Great question. I don't think we have a talk on pulsar searching. We can talk later if you like, but the short version is that you don't know, so you have to search. And that means you take those time series and one function of frequency. So here we're looking at a bandwidth of roughly 1,000 megahertz to 1,700 megahertz. And you can't make out all the profiles because there's this thing in here called scintillation, which is amplitude modulation as a function of frequency. But when we observe across large bandwidths, as we do now, you'd also want to form these folded profiles as a function of frequency and keep that frequency resolution. So in our timing measurements, the data that we collect is in the form of a cube. And there are actually several cubes. So we've seen that rotational phase axis, 0 to 1. I just showed you that you form those profiles as a function of observing time. Maybe you dump them every minute or so. And then, of course, also as a function of radio frequency if you're observing in a broad bandwidth. We're not going to talk anything about polarization, but you can also form the polarization products, which you heard about collecting polarizations, I think, yesterday as well. So basically, whenever you're analyzing pulsar timing data, it's going to come in this kind of form. Yep.
So initially we have seen the ideal train of pulses, and we associated the peak of the pulse with a time, which we called as
radio frequency axis. You'll hear words like channels or subbands, and there will be n-chan channels across your frequency. Across the observing time, we talk about integrations or sub-integration or sub-ints, and there will be n sub-integrations. Rotational phase bins. You know, binning is a thing in general, but when we just say bins, we're usually talking about rotational phase bins or profile bins. And when we talk about polarization products, you'll hear the word Stokes parameters or coherence parameters, and there's n-pole polarization. And I think you'll deal with this kind of thing in today's PS archive activity. Okay, so how do we get those TOAs? How do we measure them? And in fact, how many should we measure? We have all these profiles in this data cube. Should we measure one per subint, one per frequency channel, one per polarization? And the quick answers to those questions are, well, it's going to depend on your needs, right? If you have a short binary a short binary pulsar, or some short timescale variation that you want to probe, you're going to require to measure TOAs with a high cadence. For PTAs, pulsar timing arrays, we only care about measuring a TOA basically once every couple of weeks, so we just need one, and that's it. But should we keep the frequency resolution? That's a great question, which we'll get back to. If you keep the frequency resolution and measure TOAs in every frequency channel, the bad news is that you'll get very many TOAs. That can help you diagnose some ISM effects from the interstellar medium, this thing called pulse jitter, the shape change of the profile with frequency. But in principle, you can deal with these things and still measure just one TOA by using what's called wideband methods, which we'll get to at the end of the talk. And polarization, in practice, nobody actually is using the polarization information nowadays to measure TOAs, but there is a precedent for this. Willem van Straten has a couple papers on doing this. It's called matrix template matching. And you're not measuring a TOA per polarization, but rather you're leveraging the polarization data to measure a more precise time of arrival. Questions?
Is there any danger of creating like too many TOAs? Like, could it be a bad thing? Or?
Yes. I mean, I'm selling you a product in my answer, but I would say yes. Especially with things like PTA experiments, right? You're going to need hundreds of pulsars. You're going to need to measure them over tens of years, many times, in broad bandwidths. Forget it. And then you want to dump millions of TOAs into some computer and have it give you an answer. It's very complicated, very computationally expensive. So the answer could be yes. I'm selling you a product. Some people would say no. And then there are, of course, methods that actually try to get around the whole TOA measurement thing entirely, which I'll mention also later. So now coming back to the nitty-gritty, how are the TOAs actually measured? And the basic idea is just a cross-correlation. It's been done since the very first time arrival was measured in 1960-something, 68, 69, 70, whenever it was. And basically, a cross-correlation, right? You have your data, and you have your template, and right now these things are not very correlated, so you start shifting them, still not very correlated, still not very correlated, a little more correlated, and then there's a phase offset at which point they're maximally correlated. And that phase offset is going to be your TOA. So in part, I hope that answers your question. You're not actually choosing a point on the pulsar to measure the distance from. You're actually doing an entire cross-correlation, which is going to leverage all the information in the pulse profile. And that offset, this phase offset phi, is related to the TOA. You basically just multiply this number times the instantaneous spin period, and you add that number to the start time of your observation, and boom, shakalaka, you have the time of arrival. It's almost that easy, okay? So we have dancing and we have adding. It's not too complicated. Pop quiz number 2. This one, question before the pop quiz.
Maybe you mentioned this, but does the template also contain a model of the noise, or is it just an idealized, pristine profile?
Another fabulous question. Again, I'm trying to sell you a product and saying that mostly we want a noise-free template. That ideally you want a noise-free template. Historically, people have used templates that have some level of noise. There's no model of the noise in the template, though. The measurement of the noise and the modeling of the noise comes later in the timing model. Good question. Another question. Love it.
So is the template based on like physical information that we know, or just from previous observations?
Yes, both. And we'll get back to that towards the end of the talk as well. So hold that question and ask me again if it's there.
Yeah, can we just focus on this slide for us?
Oh yeah, sure, go ahead.
The absolute start time of the data profile, where is is that like this? Oh, okay.
Yeah, let's say it's here. Let's say I just turned on my back-end instruments and started collecting data. So this is time 0, and the observatory clock tells me exactly what time it is in UTC.
Yeah, so what confuses me is that the phase difference that you're measuring is between the template and the data. So how does it relate to?
Yeah, all right, how do I explain this easily? This template is, in this case, is the prediction for when this thing should arrive. So if there were no problem with my timing model, this thing, the data would have showed up right on top of it. There would be no delay. And so the time of arrival would be exactly whatever the start time was that my observatory clock said.
Yeah.
But it showed up a little bit later. So the time of arrival of this pulsar is actually a little bit later.
Okay.
We can go over this many times. I mean,
Yeah.
I don't know whoever got it on the first attempt. I certainly didn't. Any other quick questions? All right. Pop quiz number 2. This is a difficult one, but a major take-home point in my opinion. What is the measurement of a TOA ultimately a proxy for in pulsar timing? Who doesn't know what I mean by proxy? Okay. Proxy is, most measurements in science are proxy. That means it's a measurement that stands in for the quantity of interest. So if somebody goes out into the field, cuts down a tree, and starts measuring the distance between tree rings, and then they say something about temperature or waterfall, how much water fell, this kind of thing. You didn't measure those things, right? You measure the distance between tree rings. That's a proxy for some other thing, right? So we just talked about this measurement of a phase offset in this average profile. This is a proxy for something. What is it a proxy for? is it a proxy for the arrival time of one single pulse of radiation emitted in the nth rotation of the neutron star? Maybe it's the 5th rotation. Or is it the average arrival time of many pulses of radiation, so many rotations of this pulsar and its radiation averaged together? Is it the average arrival time around the nth rotation? So maybe the 5th rotation plus or minus 3 or something like this. Or is it the time of passage of the same fiducial longitude on the neutron star surface across your line of sight in the nth rotation of the neutron star? Or is it the time that the pulse of radiation left the neutron star? And again, take 10 to 30 seconds, think about this, talk with your neighbor if you want, and then I will ask for a raise of hand. Oh, we have a brave member of the audience?
Well, no, I have a point of clarification. What does fiducial mean?
Oh. Arbitrarily chosen. So I can draw a line of longitude on the neutron star surface and say I want to measure everything relative to the passage of that longitude across my line of sight.
Yeah.
You can draw it anywhere, right? It's arbitrary choice. Who thinks it's A? Who thinks it's B? I'll turn around so nobody has to. I'm not judging anybody. Who thinks it's C? Who thinks it's D? Okay, I would argue it is importantly C. Okay, we're trying to model the rotation of the neutron star.
In principle.
I'm sorry?
In principle.
In principle, ultimately a proxy. This is ultimately the thing we want to know, right? If I carve out a line of longitude on the neutron star surface, at what time does that longitude cross my line of sight? The whole emission process thing is how the clock works. And we have to model all sorts of noise and delays about that emission and how it gets to the observatory. What we care about, though, is when does that neutron star turn? This is very important. So I would say that the two most important take-home messages about TOAs, number 2, which we haven't talked about, is basically forget TOAs. The next generation of pulsar timing may try to avoid measuring TOAs directly. And there's some papers by Linley and Tati et al. On this subject. But the other take-home is what are TOAs a substitute measurement for? We are absolutely interested in trying to measure the passage of time of a point on the neutron star surface. Okay, more nitty-gritty about how to measure the TOA.
I have a question.
Oh, yeah.
Sorry. Can we go back to where you first introduced TOAs?
Sure. I don't even know where that was.
Yeah.
This one?
So, is the template your model? So
Yes.
So you would want your TOA to be 0 if your model is correct?
Thank you for asking this question. So I've used model in 2 different ways, very confusingly actually. Here, yeah, the template is the model for your pulse profile shape. And when I said if your model is correct, what I meant was your pulsar timing model that describes how the pulsar rotates. We haven't even gotten there yet. So that was a big mistake for me to use that word in 2 different ways. So thank you for bringing up this question. So yeah, you want this offset to be 0. That tells you that you've accurately predicted the arrival time of the next pulse. You've stayed in step with the beat. If there is a phase offset, maybe it's just noise, maybe it's a systematic offset that you can correct for. But if everything is right, these 2 things are going to lay on top of each other. Thank you. Another one.
So maybe next. So how does the signal to noise ratio scale with number of folds? Is it square root of number of folds?
Roughly, yes. Okay, so some nitty gritty about how this is done. Was that a question? No, it's not here. Okay. Same thing, same little graphic here. We're putting it in a bit of a mathematical form. So D sub j is the data profile, and you have an integer number of phase bins, and that phase bin is indexed by j. And the template, which is the model for the shape of this thing, is called peak. But you actually want to do this in the Fourier domain for reasons I won't discuss in detail. So D sub k and P sub k, the Fourier transforms of that thing. And A is the scaling amplitude. Maybe the size of this doesn't match exactly. You just have to multiply it by some number. So there's a very simple parameter that just tells you to multiply your template overall by some number. The phase offset is the thing we care about. And K is the conjugate of J. It's the Fourier harmonic index. So if you've done any Fourier analysis, you're following along. If not, not too important. Sigma is how big the noise level is in the data. It's this term here. So this formulation you'll see a lot if you do, if you want to write down the likelihood of something. It's just the data minus some the model that's altered in a way. And the way we're altering the model is multiplying by a scaling factor and multiplying by this complex phasor term, which contains the phase offset. This whole thing is sometimes called a chi-squared statistic. It's related to this quantity called the log likelihood, and that tells you how likely it is to observe the data given the two parameters. And that likelihood, that log likelihood, will be optimal, will be the biggest quantity when the parameters are such that these two things lie on top of one another. Okay, so I'm not going to talk too much about that in detail, but turns out, like I said, we're not doing this cross correlation in the time domain. Ooh, what's happening? Because cross correlations on a computer are computationally expensive, so we like to do it in the Fourier domain. This thing is called a phasor, and the reason why this looks so strange is that it's a theorem from Fourier analysis called the Fourier shift theorem. And this was kind of first written down in this form in 1992 by Nobel Prize winner Joe Taylor, and probably nobody says this anymore, but it was a previous generation thing. FFT fit was basically this method of measuring a TOA, sometimes referred to as a phase gradient algorithm, which you might come across later in your activity. But this function is nonlinear in phi, which means you can't just easily solve for this mathematically. You have to use a computer, an optimization routine to find the best fit parameter for phi. So there are other techniques, but this is the most common. Okay, but measuring the TOA is one thing, but we have to know, what's the uncertainty on that measurement, right? No measurement in science you should take at face value without an uncertainty. So you can estimate the formal TOA uncertainty by taking a second derivative of that function I just showed you, but we expect the TOA error to be related to the observable or known quantities having to do with our observation. So it goes like this, and you saw something like this, I think, in James's talk. The TOA uncertainty, or the precision to which you can measure TOA, is related to these quantities in this way. This is related to something called the radiometer equation. So a pulse period might be typical of 4 milliseconds. Duty cycle is the amount of the relative amount of time that the pulsar is on, so how narrow the pulse profile is. The system temperature of your total telescope system, 20K would be amazing. Telescope gain, 2 Kelvin per Jansky. This is roughly a GBT in sensitivity. You want this number to be big. Tells you kind of how much you can turn up your signal. It also is related to the geometry, so a bigger telescope that focuses things a lot has a very big gain. A typical pulsar flux density is about a millijansky. You might observe for 20 minutes or so. You might observe in hundreds of megahertz of bandwidth, and you might sum both of your polarizations. And if you did that, you get a 200 nanosecond TOA that would be great for pulsar timing experiments. This is not really typical, but in lots of our bright pulsars, we get this at the GBT telescope. All right. So lots of things could cause the true TOA uncertainty. So really having to do with determining the epoch of passage of that longitude could inflate these error bars. They could be bigger than the formal TOA uncertainty. They could be bigger than what we expect here, for a whole bunch of reasons, which are maybe too boring to talk about right now since I'm behind schedule. Here's a plot of very many different pulse profiles for a number of pulsars in the nanograph sample. The two different colors are two different frequency bands. The point here is just to see that pulse profile shapes come in a huge variety, especially in the millisecond pulsar class. And what you want, though, is very sharp features. So sharp, narrow things, even if it's just in a piece of the pulse profile, because the duty cycle is very important. But just having sharp features allows you to very finely make that cross correlation, which means your TOA uncertainty will be better. So what do TOAs look like in practice? Very old school TOAs look like this. We just write them down in an ASCII text file. And the important quantities are where was the TOA made, so what observatory, this is a code. What radio frequency were they made at, this is 370 megahertz. What is the pulse time of arrival in modified Julian date here, in probably UTC coordinates. And what is the measurement uncertainty, so what is that error on the time of arrival. But modern pulse TOA measurements are a lot more complicated. There's a lot more information, usually having to do with how many, let's say, phase bins were in the profile, how good of a fit was the TOA, what was the signal to noise ratio of the observation, all this other stuff, metadata to the TOA. Okay, so here's the super basic picture I hope that we've arrived at right now. We have a rotating pulsar emitting pulses. They traverse space and arrive at our telescope. And recall that the thing is just spinning and spinning down. So we can write down the function for that, right? There's a spin period at some point in time, and f dot, how fast it's spinning down. You just write down the whole frequency evolution for all time. Integrate this equation, very simple to do, and you get an expression for the phase of rotation of the pulsar as a function of time. Well, that's a timing model. We just want to know what rotation the neutron star is currently at some given time. You would be done if life were this simple, but as it turns out, this is not reality, right? There's not just a pulsar sitting there and we're sitting here on Earth in the same reference frame staring at it. We are not in an inertial frame with respect to the rotating neutron star. So most millisecond pulsars are in a binary, so it's going around in an orbit. Obviously, we are going around in an orbit, and there's all this stuff in between us called the interstellar medium that also changes the arrival time of the TOA. So there are very many delays that need to be applied to the observed TOA quantities in order to put them into an inertial reference frame, and that inertial reference frame is the solar system barycenter. But of course, if the binary is also if the pulsar is in a binary, you also have to correct for that non-inertial motion in order to basically make it like this picture here. So you have to correct for things relating to each one of these patterns. But this first transformation, referring the TOAs to the solar system barycenter, so it's as though we're stationary with respect to, or in an inertial frame with respect to the pulsar, can be a bit confusing. Still a little bit confusing even to me. There are two kinds of transformations that happen to the TOAs. The first one is a time transfer. So you measure your TOA with respect to the time at the observatory clock. That gets referenced to GPS, which then gets updated to a very accurate UTC time. And then you transform that to barycentric dynamical time. I think this is in French, so you read it backwards. Excuse me for making that comment. But you can think of barycentric dynamical time as the time some clock reads which is co-moving at the location of the solar system barycenter, but which is free from the whole gravity of the solar system. It's a little confusing, but it's basically like I can have a clock right here that is reading off the time of this imaginary clock, right? I can have it right here, and maybe I'm observing some pulses from the pulsar right now, and I can just write down those times. They would be in TdB units. In practice, that's not what's done. We use the observatory clock, and we make this coordinate transformation, this unit conversion, if you will. It's a little bit like a time zone correction, right? You can be in the same place and just know the time somewhere else. But you also need to correct for the fact that you have to pretend that the pulses arrived at the barycenter. So that's a geometrical correction. You're actually first kind of correcting for the spin of the Earth and the location of the observatory on the Earth to the center of the Earth, then referring it to the solar system barycenter. You need models for the entire Earth and its spin and the solar system in order to do that accurately. So this is kind of how we put TOAs into the reference frame of the solar system barycenter. But coming back to these three panels and how various components in them show up in the timing model, which all of these will ultimately be components in the timing model instead of just having the spin and spin down. Again, if it's in an orbit, you'll have orbital elements. You'll have your 5 Keplerian parameters, the orbital period, the projected semi-major axis, the epoch of passage, the orientation of the orbit, and the eccentricity. That's roughly the 5. That whole system may be moving across the sky, and so you may see changes in those parameters. You may see the projected semi-major axis change. You may see the orbital period change for some reason. But there's timing noise too. This clock is not a perfect clock, and so there's a process which adds noise to the clock, which we call timing noise.
You might say this word was secular variation.
This thing?
No, the third point in your pulsar.
Below.
Yeah, if you go down. Secular variation.
Oh, yeah. I was just, okay. So pretend that this whole system is also moving with respect to the solar system barycenter. The projected semi-major axis could change as it moves across your line of sight. What's another thing?
Is that referring to how the rotational axis is like the...
It is, you know what? Come ask me later, because it's actually...
The whole thing moves with respect to the...
Yeah, this whole thing moves with respect to the solar system.
And that's
So,
what
yeah. So that's saying that what the binary looks like and how your times of arrive at the telescope changes because of the slow motion of the system with respect to the solar system. Thank you for allowing me to clarify that. So in the interstellar medium, we have dispersion, which I think we talked about yesterday a little bit. This arises from a varying index of refraction and multipath propagation, which results in broadening of the pulse profile, and also twinkling, which was that amplitude modulation I showed you in the frequency plot of pulse profiles. But in the solar system, like I said, we have to know these things, make those clock corrections. We have to refer the TOAs to the barycenter by using a combination of the model for the Earth and its place, its rotation, as well as the location of all the planets and the sun and their masses. But we also have to model the position of the pulsar on the sky, because where we are in the solar system will induce a slightly different delay based on where the pulsar is on the sky and its proper motion. So because that whole source moves across the sky, that means its position is changing. So this is basically just the change in position. And the parallax arises from the fact that the source is not at infinity. So the wave fronts of the pulses are actually curved, and you can see that change, that delay in time on either side of the sun via parallax. I'm sorry? Oh, yeah, Chris.
So when we make the correction for the solar system barycenter, is that just a correction to time of arrival, or do we also correct the pulse profile?
So, how to think about that? Definitely yes to the first part. There's probably a way to think about it that you're also changing your pulse profile data. You could make that correction too. In practice, that's not what we do. We measure the times of arrival as they are observed at the observatory, and we correct the times of arrival. So if you have any of these terms wrong, they induce systematics in your times of arrival. And when you subtract out what you think is the rotation of the neutron star, you will get large trends in what are called pulsar residuals, which is just the difference between the model and the timing model and your set of pulse times of arrival. And so if you have the frequency wrong in the spin period of the pulsar, you'll have a linear ramp, you'll have a quadratic trend. If you have the pulse frequency derivative wrong, you'll have a 1-year sinusoid if you have the position of the pulsar wrong, and that 1 year obviously has something to do with the Earth going around the sun. And if you have the proper motion wrong, you have this same exact 1-year trend, but it linearly increases as a function of time. Because maybe you have it exactly right now, but then it moves. So that error basically linearly increases as a function of time. If you have the parallax wrong, you'll get a 6-month modulation because the parallax is measured on either side of the sun, so it's 1 year divided by 2. And then if you have the binary periods wrong, you have a lot more funkier shapes. Okay, so coming from the interstellar medium, how does this affect the pulse profiles, which in turn affect the pulse times of arrival? Just the fact that you have an ionized interstellar medium, you have free electrons, that's a refractive matter, which means at higher frequencies, at lower frequencies, the pulses take longer to propagate, so they have a delay relative to higher frequencies. And the quantity of interest there is called the dispersion measure, which we'll come back to later. But also, because the interstellar medium is not perfectly homogeneous, you have multipath propagation, which tends to broaden the pulse profile shape as a function of frequency. This is something also that you will need to account for in order to get a very accurate pulse time of arrival. If you're lucky and you have a binary system, a binary pulsar, you don't just have the 5 Keplerian orbital parameters, you have post-Keplerian parameters, some of which, all of which here actually arise from GR, or some theory of gravity, but I think as written here, these are GR. And you probably heard about, let's say, the precession in the orbit of Mercury, which was this fabulous prediction by Einstein. So we have to also model the relativistic precession of the orbit in some of these binary pulsars. The Shapiro delays the extra amount of time it takes for the pulse to traverse the gravitational potential of the companion star, combination of gravitational redshift and time dilation. So as the pulsar clock moves in and out of the companion's gravitational potential, we call this the Einstein delay. And then, of course, we know about gravitational waves now. A binary will shrink due to the radiation of gravitational waves, so that will change the orbital period. Shouldn't that be θ? Well, anyway, we can also model the gravitational radiation, and this is basically what got pulsars its second Nobel Prize in 1993, the indirect detection, or the first evidence of gravitational waves. Okay, any quick questions? Otherwise, I will continue. All right, so the schematic of making of a timing model, which again, the timing model is the description of how the neutron star rotates. We first make that transformation to a frame of reference which just has the time of arrival, just has the neutron star spinning in it with respect to the solar system barycenter observatory. So you make all these corrections. There are lots of delay terms, and most of these terms are functions of the timing model parameters. So all these other things, like let's say all these parameters and so on, they may be part of the function describing this delay term here, the binary motion. But like I said, there are clock corrections. These delays are local to the solar system. This one is that dispersive delay. This one has to do with the secular motion of the pulsar across the sky. So once you've corrected to the frame of just having a spinning down pulsar, then you have that basic equation we wrote down before, and that's the phase evolution of describing the rotation of the neutron star. And now you're in the proper frame of reference, so that you can just write it down like this. And then you compare your prediction for the phase of the neutron star with the observed quantity. So you're saying this was the 112th rotation of the pulsar. Maybe this number is 112.0001, and that difference we call a residual. You divide it by the spin frequency of the instantaneous spin frequency of the pulsar to get units of time. And so you take these residuals, well, they're part of the likelihood function that you plug into some optimization routine in order to minimize the same it's also a chi-squared statistic. This is different from the one I showed you before, but the idea is the same. You want to write down just the difference between a model and data and optimize it in order to get the best fit timing model parameters. And this is where it really gets tricky. This is where our timing codes, tempo, tempo2, pint, enterprise, tempo nest, that's where these come in. Yeah, question?
I noticed that we only care about first derivative. Do we sometimes go to second derivative direction?
Yeah, sometimes, yes. And that's really tricky and not a topic I want to spend time on right now, but we can talk later. It's really tricky. All right, so here's what a timing model looks like if you read one in a paper. Very many lines. I won't go through all of them, but you have position, the spin frequency, the proper motion, the orbital parameters, and so on. These are derived quantities. But hey, this is 14 digits of precision. This is why we're all here, right? Pulsar timing is really special in astrophysics. We deal with an empirical science. We want to be a laboratory science, right? We want to be like laboratory physics, be able to control our experiment, make really precise, accurate measurements. That's really hard to do in most empirical sciences, like astronomy. Pulsar timing is really an exception. You can do this because of the nature of neutron stars and the fact that basically rotations come in integers. Okay, so turning along, because I'm running out of time, you have to look at the residuals. And those residuals, like I said, are just what's left after subtracting your timing model from your predicted, from your observed time of arrivals. And the residuals are a combination of systematic and random errors, and that may arise from radiometer noise, so your telescope and its instruments. There could be an error in your timing model. Don't worry about the parenthetical things for now. There could be unmitigated effects from the interstellar medium, noise from pulse jitter, which is basically like, think of it this way, if you have a Gaussian distribution with 0 mean and 1 standard deviation, if you pull a finite sample from that distribution and make a new distribution, it will not have 0 mean and it will not have a variance of 1. That's basically pulse jitter, as I will tell you. So the fact that you have a finite sample of pulses gives you noise. There's that true timing noise. No clocks are perfect, so you have a drift in the pulse period. It's a random walk in pulse period or pulse period derivative or phase. The point is that the clock drifts with time. It's not a perfect clock. And you could also have gravitational loosening. So you can use a very complex Bayesian machinery to model all these sources of noise and at the same time fix your timing model and get the best timing model fit. Yeah, question?
So working in the light period now.
All right, so we're getting there in like 2 slides. Hold your question, please, but it's coming. I'm not going to spend time here because I showed this plot again in my activity, but schematically this is how you carry out pulsar timing. You have your TOAs. We talked about all these things that are part of the TOAs. You have your timing model. We talked about many of these things which are part of the timing model, and they just fall into different categories. You put them together, subtract them, you get residuals, and you use some software in order to optimize that to get the best parameters, and then you iterate. Here's what some residuals look like in practice. This is from Nanograv, the 9-year data set. This long, trendy looking thing, this is timing noise. It could be timing noise. We'll call it timing noise here, because I know it is. But after we whiten the timing noise, meaning make it flat, it looks something like this. Don't worry about this bottom panel. We'll come back to that. And this is just another pulsar. But quickly, I just want to show you, hey, some results from the IPTA, because that's why we're here, the IPTA, right? So Ben Pereira and a whole bunch of other people are finalizing the data release 2 paper from the IPTA. Here are all the residuals, half the residuals from the pulsars in that data release. You can see many of them have lots of timing noise. That's bad. We like nice, flat, white-looking residuals. Here's the other set. I have no idea why we time it. I know why we do, but that's a big trend there. All right, so coming back to your question, why are the residuals different from 0? Well, you can have systematic errors, and we know that all models are wrong, but some models are useful. This means that maybe one of your timing model parameters has the wrong value, maybe a timing model parameter is missing from the model, or maybe your model choice is bad and you need to you actually have to change the whole version of the type of model that you're using. But a lot of it is just random stochastic measurement uncertainty or some other kind of process that adds randomness into your data. And this is a funny quote: "The generation of random numbers is too important to be left to chance." But more importantly, you can't actually ever really pretend that random sources of error can be described by a deterministic way, right? You shouldn't do that. And I think this was John von Neumann, who was a Hungarian. So anyway, random errors just mean stochastic uncertainties of various origins. And timing, there could be true noise, right? It could be some quantum noise, an irreducible uncertainty. That's a largely philosophical question, so we're going to skip it. This is classic timing model stuff. You just correct parameters in your model. You hear a lot about noise modeling nowadays in pulsar timing. What is the noise model? No time to deal with that in detail, but it's super important. That's where all of the gravitational wave stuff lies, buried in the noise. So you have to understand all of your sources of random error very well in order to dig out some other signal. So noise modeling sounds boring. It's where the Nobel Prizes are. I don't think we're going to get it. Anyway, and a quick note on noise. Like I said, it's stochastic variations. Not all noise is the same. This is very important because it allows you to differentiate between the sources of noise. So classically, you can differentiate between signals because they have different functional forms, a predictable function. We hope that each source of noise has a different statistical description, and each of those can be individually separable in a similar way to the classical deterministic signals can be separable. But physically describing what those noise sources are can be challenging.
So you want additive noise?
I'm sorry?
You want additive noise?
Yeah. I'm sorry, I have to pick up the pace because, but don't stop with the questions if you have them. And I'm coming back to your red-white noise. Two broad classes of noise. You have Gaussian noise, non-Gaussian noise. You hear about this a lot. You can read that for yourself. But the other kind of noise you hear a lot about is white noise and red noise. This differentiation has to do with the distribution of your samples of residuals, let's say. This categorization has to do with the correlations in a sequence of samples. They are totally different. Do not confuse them. This is another major take-home, right? Gaussian noise, non-Gaussian noise, distribution of the samples. White noise, red noise has something to do with how the samples are correlated, let's say as a function of time. Doesn't have to be that. Red noise is called red because it has lots of power at low frequencies. What that means is that each point is likely to be close to the next point. White noise, there is no such correlation. So a point here, the next point over could be anywhere. Okay, in context of pulsar timing, white noise may come from, like I said, the radiometer, pulse jitter, the interstellar medium. Red noise can arise from timing noise, DM variations, or the gravitational waves. Pop quiz 3. Timing noise is, who thinks it's red? Who thinks it's white? Both? Neither. It's blue. Oh, stop. Okay, that's interesting, because here I just said timing noise is red. A lot of people said both. Some people said white. I would actually say that there's a case to say that it's actually both, because you could probably argue that it's a sum of red and white noise. But let's not talk about that too much, because there's still many slides left, and I have 8 minutes. All right, so we're back here at our basic picture, and we want to spend a little time now talking about this portion, the dispersion measure. It is simply the integrated column density of free electrons along the line of sight. And it induces a time delay that's proportional to the radio frequency to the -2 power. In reality, what we've been learning is that the column of electrons that you probe is a function of time, and the path that the rays take through the interstellar medium is also a function of time, but also a function of frequency. Therefore, this term is also a function of both of those things. But for simplicity, we will just talk about time variations of the dispersion measure. So you can very precisely measure the DM as a function of time. You see lots of trends. They mean different things in different pulsars, but this allows you to probe the interstellar medium. And the reason why we can measure the DM so precisely is, if you remember way back to those various millisecond pulse profiles that I showed you at 2 different frequencies, we can measure the time of arrival at 2 different frequency bands and decompose their TOA into a common component, some offset that's common to both of them, and some separation that is proportional to their frequency separation to the -2, which is the dispersive delay. And the wider apart you are, the bigger the lever, the more precisely you can measure the DM. So the question now is, how can we improve pulsar timing? And I'm writing down again a form of the uncertainty on the TOA. So you want to get this number as small as possible. You can tweak these parameters, but you run into these various problems. And the one I want to focus on is that there are new instrumentations that are broader bandwidths. They should allow you to measure TOAs more and more precisely. And some of the new telescopes have such capabilities. Yesterday, you did some real-time observing with the ultra-wide receiver at Parkes. Effelsberg also has one. Meerkat has a very sensitive broad bandwidth system. At the lower frequency end, Chime has a large fractional bandwidth. LOFAR is a very large array of low-frequency antennas, and Menufar is similar to LOFAR. And these have very broad bandwidth observations. So with great bandwidth comes great responsibility, though. And what this means is, now that you can observe the pulse profile across frequency, you will have to account for the fact that the pulse profile shape changes with frequency, and you will have to account for the fact that the DM changes as a function of time, which I just showed you. So back in the day when we didn't have broad bandwidths, it was still appropriate to just do this simple cross correlation. But if you sum your entire frequency band and do this, you will sacrifice timing precision because you've averaged over some of these effects instead of accounting for them. So what we do in Nanorev right now is we actually make many TOA measurements as a function of frequency, and that's too many TOAs, like I said before. So we've developed this new methodology to still extract a single TOA, but accounting for the dispersion measure sweep as well as the shape of the profile, how the shape of the profile changes with frequency. We call this wideband timing, and in summary, you're substituting, instead of having a single 1D template for measuring a TOA, you have an evolving template with frequency, this two-dimensional thing. And here's the wideband TOA likelihood. It looks exactly the same, except there's this new index N, which indexes the frequency channel, so you've maintained frequency resolution. That phase term there is still just the phase offsets, so it's basically a cross correlation in each and every channel. But these very many phase offsets are constrained by the DM relation, so you extract the common mode and the DM parameter. So that's it. You get a measurement of a TOA and a DM. And also, I won't spend time on this, but it basically accounts for the most common interstellar medium effects, because you're also fitting for an amplitude as a function of frequency, so you account for scintillation. You saw how it accounts for dispersion. And more recently, I've added a term here that accounts for the pulse broadening, which is called scattering. And yeah, that's all I'll say about that. And in an earlier paper, we showed that you can actually improve the TOA and DM uncertainties if you account for pulse profile evolution. That's the summary of this slide. I'm sorry, I'm sprinting now. But I did start like 5 or 7 minutes late. All right, so give me just a few more because I want to get to 1 or 2 more fun slides. No more music, but so here's what multi-frequency TOAs look like in the nanograph data sets. Here's what the wideband data set looks like. So very, factor of 30 fewer TOAs and a whole bunch of DM measurements. And we have to update basically how we do pulsar timing in order to optimize the use of these these measurements. I never told you though how to make the model, and there was an earlier question about that, even in the one-dimensional way. How do we do that? But in the meantime, I have Pop Quiz 4, and I'll just tell you the answer to this, which is that wideband timing methods help to solve problems having to do with profile evolution, the interstellar medium, and data volume. So the answer is B. So how do I make a noise-free profile template? And in the one-dimensional case, you could simply just use an analytic function like a Gaussian profile. We saw that many pulse profiles have a simple shape. Many of them don't, though. So maybe you're going to average all your data together and smooth it, pass it through a low-pass filter, something like that. But how do you make a noise-free profile template that evolves with frequency? How do you do that intelligently? Well, you could use evolving Gaussians. I've tried that. Don't spend your life trying that. Or you can come up with something that's more data-driven and better suited for general purposes. So I'm going to talk you through how this works very quickly. But here's the original pulsar observed by Nenufar in a similar frequency band as the original LGM1 was observed by Jocelyn Bell. And here are traces of the pulse profile shape at these frequencies. And you can see how different they are, right? So if you want to make that wideband TOA measurement, you have to account for that pulse profile evolution. How does it work? All right, so you want to make use of the fact that the profile here is very correlated to the profile in the next channel, right? So think of this as a high-dimensional vector in a vector space of n bins, right? So maybe there's 512 measurements across the profile. Here's the profile vector at some frequency. Well, at the next frequency over, the profile vector isn't here, right? It's here. Okay, and then you go to lower frequencies and it's here, and lower frequencies and lower. Okay, so that's just a simple continuous curve. Why not just decompose this data using principal component analysis? We can talk about that later if you're not familiar with that term. But basically, it uses a subspace of that 512, that vector space that's 512 dimensions to project the data onto these basis functions, and then you simply parameterize that simple curve instead of accounting for variations in all 512 phase bins or something silly like that. And that movie is showing you what this model looks like in the 3-dimensional cube of this reduced subspace here. That probably made no sense, but I'm sorry, I have to hurry now. We're coming close to the end. I referred to this earlier. There are new methods that are attempting to just do away with TOAs as an intermediate product of pulsar timing. This is called profile domain timing. It's work done by Lenley Lintati, Vladimir Van Hasteren, and other people. But the take-home measure is that maybe you can just go from the profiles, the folded profiles, straight to a timing model and residuals. Don't have to make TOAs. It's very complicated and it requires a lot of computing power. That's why I think, for the time being, practical TOA measurement will still be necessary for some time in the future. We're going to skip this because Andre has an entire talk on it, but I just like to say the PTA experiment is a really beautiful experiment. When you talk about relativity, if you take a basic class in special relativity, they're always talking about clocks that are situated in a grid. That's what a pulsar timing array is, right? So it's really a classic kind of Einsteinian experiment. So we're just going to skip all this and go right to the IPTA, which is one PTA experiment, which I don't think anybody introduced yet. So here it is. These are the very many telescopes involved in the IPTA and the very many countries. And there are new ones coming online, new telescopes. and new collaborations, but it's not my place to introduce all of them. And I also won't introduce Nanograv at the moment. I just wanted to show you this curve is. So I have one more question for you, but it's not gonna make sense without introducing the pulsar time array experiment. So forgive me for going over time and skipping the pulsar time array section, but you have a whole talk by Andre on that, and you have a whole talk on Friday by Maura McLaughlin, which will tell you all of the interesting stuff that I had to skip over, but it's all the stuff that we use pulsar timing for. So probing interstellar medium, measuring neutron star masses, binary evolution, things related to gravity and gravitational waves, planetary systems. The list goes on. This is why the field is really so exciting. So stick around, pay attention. This is going to be 2 really great talks about why you just sat through this 90-minute lecture is really so great. So thank you.